Good morning, this is Dr. Jingbo Louise Liu. From today, we start your chapter 7 about quantum theory and atomic structures. In this class, we are going to discuss the nature of the light and the wave-particle duality. Correspondingly, we are going to do the unit conversion from the frequency to wavelengths to energy. And then the last topic, we are going to discuss quantum mechanical model of the atoms. There is one more topic about atomic spectra. We are not going to discuss it, but there is no harm for you to know. The first topic is about the wave nature of the light. The visible light is a type or part of your electromagnetic radiation. The wave properties of the electromagnetic radiation are discussed by 3 variables. Totally, there are 4 different variables. We are going to focus on 3. The first one, frequency. Second one, the wavelength. The third one called amplitude. There is one more called polarization. The frequency is defined as the occurrence of the repeating cycle per time unit. Normally, you use a per second to measure it. Per second is also known as hertz. The second terminology is called wavelengths. Wavelengths, you use a smaller lambda to denote it. The wavelength is the distance of the wave, of a wave which travels in one cycle. Usually is the distance between the adjacent of the crest or the adjacent of 2 waves trough. The unit, the SI unit, normally is in meters. The amplitude is the height of your wave crest or the depth of the wave trough. Usually the amplitude represents or measures the intensity of your light. The higher the amplitude, the brighter the light is. The lower the amplitude, the darker the light is. So how do you correlating the frequency gamma and the wavelength lambda? You are going to use the speed of light. The speed of light in vacuum usually is a constant value, 3.00 times 10 to the power 8 meters per second. Your light, speed of the light, C equals the gamma times lambda. We are going to show you how to define all these different terminologies. So your frequency, the frequency, if you count, say, per time unit, let's assume this is a per second. Whatever I showed you, A, B, C, 3 different waves, so they have per second. So how many cycles traveled? Let's start from the crest. This is a 1/4, half of it, and then 3/4, and then finish it. This is a 1 cycle, and then followed by the second cycle. So that's called the frequency. Let's say what's the wavelength. If you go to the crest for the first wave, you can go from over here, so go to the crest and to the adjacent crest. So that's your wavelength. It's a distance. Your A, B, C, you can see you have 3 different waves. So the wavelength for A is almost, I think is exactly twice of your wavelength of your B, lambda B, and it's 4 times of wavelength of your C. So your frequency is reciprocal to the wavelength. So your frequency times wavelength equals to a constant. So therefore, the A travels the slowest, B travels the fastest. So that's how you determine the wavelength and frequency. Let's move on to the amplitude. Amplitude also measures the brightness or intensity of your wave. If you have two of the waves that have the same wavelengths, but they travel differently. So one wave has the lower amplitude. The second wave has the higher amplitude. Yes, the second wave with the higher amplitude is brighter. The one with the lower amplitude, which is dimmer, that essentially showed you the wavelength and the frequency as well as the amplitude for your light. So as we already mentioned, your visible light is a portion of the electromagnetic spectrum. Electromagnetic spectrum ranging from your radio frequency to the microwave, to the infrared, to the visible light, and then ultraviolet, further X-ray, and then very high gamma ray. In terms of your visible light, you have the red light, you have the blue light or ultraviolet. So the violet has a lower wavelength, higher frequency, meaning higher energy end is in this side. So your red light has a lower frequency, larger or longer wavelengths. So it's about 750. It's a range. All of these different 7-colored light, they have the wavelengths in a certain range. It's not one value, it's a range. So we are going to do this conversion. So we are going to use these different examples to show you how we are going to interconvert wavelengths into frequency. Further, you convert it to the energy. Imagine you have a dental appointment. Your dentist uses the X-ray to take a series of dental radiographs. So while you are going to listen to the radio station, my heart will go on and on. And then you're looking outside to the blue sky to enjoy the view. My question is, what is the frequency for these 3 different wavelengths? X-ray wavelength is 1.0 angstrom. Radio frequency wavelength 325 centimeter. Blue sky wavelength equals 473 nanometers. How do you convert each of these different electromagnetic radiation into the frequency in hertz or in per second? Yes. So our plan, you are going to use the equation C equals the wavelength times the frequency. C equals wavelength lambda times the frequency gamma. And then you are going to convert wavelengths to frequency using frequency equals C divided by lambda. And then make sure your wavelengths must be in meters, must be in SI unit, because your C, speed of light, 3.0 times 10 to the power 8 meter per second. Any of the unit, angstrom, centimeter, nanometers, you must convert it into the, yes, meters. So how we are going to do this? We are going to show you. Totally you need, I would say, 2 steps. Step 1, convert any units into meters for your wavelengths. And then you apply the equation frequency equals to the C, speed of your light, divided by your lambda. Let's see. Our X-ray, you have 1.0 angstrom. How do you convert angstrom into meters? We know your angstrom, 1 angstrom equals 10 to the power -10 meters. You convert it to meters. Convert the unit of angstrom into the meters, and then you apply this value into the equation. Frequency equals C divided by lambda. C again is your speed of light, velocity of your light in the vacuum. 3.00 times 10 to the power 8 meter per second divided by 1.00 times 10 to the negative 10 meters. So you calculate your frequency. My calculation, 3 times 10 to the power 18 per second. Per second, also equivalent to hertz. Similarly, you convert your radio frequency from centimeter to meter. 1 centimeter equals 10 to the power negative 2 meters, or you divide it by 100. And then you apply 3.00 times 10 to the power 8 meter per second divided by your wavelength. Calculate your frequency. The last one about the blue sky. You need to convert nanometers to meters. 1 nanometer equals 10 to the power negative 9 meters. And then you determine your frequency. Followed by, what's the relationship between energy and frequency? Any solid object emits visible light when you heat it up at about 1,000 Kelvin. So this phenomenon for your object emits visible light. You consider this black body radiation. The color and the intensity of the light changes as long as you change the temperature. You change the temperature from 1000 K to 1500 K to 2000 K, you are going to change the color of the intensity. The color is related to the wavelength and the frequency. So while your temperature is related to the energy, therefore, the energy is related to the frequency. The energy is also related to your wavelengths. So energy can be calculated by N times H multiplied by frequency. This E, capital E, is your energy of the black body radiation. The smaller n is a positive integer. You call it principal quantum number. The H, this capital H, this H represents Planck's constant. This gamma again represents your frequency in hertz. So also, let's move on, try to further define the quantum theory of your energy, and then we are going to do the calculation of your microwave. What's the energy of the microwave if the wavelength is 1.2 centimeter? We are going to show you the example. So any object, including the atoms, can emit or can absorb energy, but the energy is only a certain quantity of the energy. This meaning the energy is quantized. The energy occurs in the fixed quantities rather than being continuous. Each fixed quantity of the energy is called quantum. It's a quantum. That's your quantum theory of the energy. An atom changes its energy state by emitting, giving out, releasing, or absorbing or taking in one or more quanta of the energy. This quanta of energy, you use delta E to represent it. This delta E equals NH gamma. That's what we already showed you. So N is the whole number. In our case, our N you figured out is 1, 2, 3, all the way to 7, corresponding to your, yes, possibly to your periodic table. Let's try an example. Calculate the energy of radiation from a certain wavelength. Imagine you are going to cook your meal. You use your microwave oven to heat it up a meal. The wavelength of this microwave radiation is 1.20 centimeter. Possibly that's what we are using in our house. What is the energy of one photon of this microwave radiation? What's our plan? If you know the frequency in centimeters, you must convert the centimeters into meters. And then you use your C equals lambda times gamma to determine your frequency. You convert your wavelength into the frequency using your speed of light. And then you calculate the energy of one photon. Simply use E equals H gamma. So consider N is 1. It's called ground state. Our solution. Step 1. E equals H gamma. Convert the gamma into C divided by lambda. And then you need to know what's your H. H is called Planck constant. Your Planck constant equals 6.626 times 10 to negative 34 joules times a second. Your light speed, you already knew, 3.0 times 10 to the power 8 meter per second. And then you convert your centimeter to meters. Calculate the energy for one photon from the radiation by your microwave. Bohr's model of the element. The simplest element is the hydrogen atom. Therefore, we use hydrogen atom as our example. Bohr's atomic model for hydrogen postulated the following. Point 1. The hydrogen atom has only certain energy levels, which Bohr called it stationary states. Each state is associated to a fixed circular orbital of the electron around your nucleus. The higher the energy level, the further the orbital is from your nuclei. When the hydrogen is in the first orbital, the atom is in the lowest energy state. This energy state you call the ground state. Be careful, ground state is different from your stationary state. Ground state is one of the stationary states with the lowest energy state. Point 2. Your atoms do not radiate energy when it's in the stationary state. The atoms changes to another stationary state only by absorbing photon or emitting photon. When you absorbing photon, you call the excitation from lower state to the higher state. The energy of your photon can be calculated by H gamma. This energy equals the difference between the energies from two energy states. When the energy of your electron is in any orbital higher than n is 1, so that atom is called in the excited state. Your electrons is not in your ground state because absorption of energy, so this n can be 2, can be 3. In this case, your hydrogen atom is in an excited state. Let's take a look. This is a commonly used Bohr's circular model. So the first one called the staircase model. So your n, which is one of the stationary state, n, one of the stationary state, if n is 1. This stationary state called ground state. If n is 2, it's called first excited state. N is 3, second excited state, etc., etc. Be also careful. When your electron comes back from higher energy orbital to the lower energy orbital, the energy will be emitted. This is called emission. And also be careful. Did you see the staircase? The differences between the staircase, they are different. The Bohr's model usually showed you in the middle you have your nuclei. The first circular, the smallest circular, is your ground state. If n is 1, it's ground state. N is 2, first excited state. 3 second excited state, 4 third excited state, and so on. The energy will be released whenever the electron comes back from the higher to lower orbital. From the first ground state, n is 2, go back to n is 1. This energy released is involved in ultraviolet. From n is 3, go to n is 2. This energy released, so that's in the infrared. Further up, so the energy will be released. Again, the energy released is different. So can be infrared, can be visible, can be also ultraviolet. In our case, we are not going to further discussing the emission of that energy, but we do need to know 4 quantum numbers and associated the shape of the orbitals. There are 3 quantum numbers. They are associated to your atomic orbitals. There is another one related to your electrons. The atomic orbital is specified by the 3 quantum numbers. First one called smaller n, principal quantum number. Second one called smaller l, your angular momentum quantum number. Third one is ml, called magnetic moment quantum number. Let's see. The principal quantum number n is the positive integers. Can be 1, 2, 3, all the way to 7 at this point. The value of n indicates the relative size of the orbital and therefore its relative distance from the nucleus. A couple minutes ago, I showed you the Bohr's circular model. So you see n is 1, n is 2, so that distance is different from the nuclei, the center of your atom, the nuclei. The second quantum number associated to your orbital is called angular momentum quantum number. You use smaller l to represent it. This smaller l is an integer, not necessarily positive, can be ranging from 0 to n-1. Remember one thing, L, angular momentum quantum number, always has one number smaller than n. If n is 2, your L has to be smaller than 2. Can be 0, can be 1. N can be different numbers. The number of L, angular momentum quantum number, indicates the shape of your orbital. The third quantum number associated to your atomic orbital is called magnetic moment quantum number, smaller ml. Is an integer. Value can be ranging from negative L, this smaller L, negative L to positive L. Can be from negative L to 0 to positive L. This value indicates the spatial orientation of your orbitals. There is another quantum number called ms. ms is representing electron spin quantum number. Electron spin quantum number defines the rotation direction of your electrons. ms, electron spin quantum number, can be only positive 1/2 or negative 1/2. I have a table, will show you, will summarize these 4 different quantum numbers. So this table 7.2 shows the hierarchy of your quantum numbers for your atomic orbital and also related to your electron spin. As we mentioned, the principal quantum number n represents the energy size, how large the energy, can be positive 1, 2, 3, all the way to 7. Let me show you an example. If this principal quantum number is number 1, your L, angular momentum quantum number, can be only 0 because 1 minus 1 is 0. In this case, your angular momentum quantum number is 0 and your magnetic moment number can be only 0. In this case, meaning you only have one orbital when L is 0. The second case, and your electron spin again for that orbital, the electron can be 2 electrons in that orbital, either 1/2 or negative 1/2. If my n principal quantum number equals 2 is 2, your L can be two numbers, can be 0 starting from 0, and then 2 minus 1, which is 1. If the L is 0, your ML again is 0. If L is 1, your ML can be negative 1, 0, and then positive 1. Meaning this you have 3 different orbitals. This orbital I will show you is called the p orbital. If my principal quantum number is 3, this 3 and then your n 3, your L angular momentum quantum number can be from 0, can be from 1 up to 3 minus 1. 3 minus 1 is 2. The first two we already know. ML can be 0. If L is 1, your ML negative 1, 0, positive 1. This represents 3 different orientations, 3 different orbitals. If your L is 2, this orbital you call the D, like in David, D orbital. S, this L is 0, you call it S orbital. L is 1, you call it P orbital. L is 2, you call it D orbital. In this case, your ML can be negative 1, start from negative 2, negative 1, 0, positive 1, positive 2. Totally, you have 5 different orbitals. So followed by, I'm going to show you a couple examples how we are going to determine the name based on the quantum numbers. So how we are going to identify the different orbital names. So if you have the value of angular momentum, quantum number, and how you are going to determine the total number of the orbitals if n is 3. So our plan, you simply determine the L from your n, because L can be ranging from 0 to n minus 1. And then your ML, determine ML. ML ranges from negative L to 0 to positive L. Let's see. If my n is 3, so your allowed value for L will be 0, 1, and 3 minus 1 is 2. When your L is 0, your ML has to be 0. This is only one case. You call this S orbital. If L is 1, your ML can be negative 1, can be 0, can be positive 1. So you have 1 orbital over here, have 3 orbitals. If your L is 2, your ML can be negative 2, negative 1, 0, positive 1, positive 2, sorry. So you have 5 orbitals. 1 plus 3 plus 5. Totally you have 9 orbitals if n equals 3. How do you determine the total number of orbitals? N to the power 2. You use n to the power 2. How do you determine the different names, as we mentioned, based on these different quantum numbers? If I have this example, my n is 3, L is 2. What's the name for this orbital? So let's summarize it. If your L is 0, the orbital called S orbital. If your L is 1, the orbital called P orbital. If L is 2, the orbital is called D orbital. If L is 3, the orbital called F orbital. Particularly, if your n is 3, your L is 2, this orbital is D orbital. But what kind of D? You put the principal quantum number 3 in front of the D. So you call it 3D. So your L is the angular momentum quantum number. This one represents different shape of orbitals. Make sure you use a smaller letter S, P, D, F to represent it. How many this D orbital you have? 3D orbital you have? Any D, 3D, 4D, you have 5. Yes, that's right. You have 5 different orbitals. So 5 different orbitals. If my n is 2, L is 0, this one called S orbital is a 2s. You only have 1 orbital, only 1 orbital. If n is 5, L is 1, this orbital is called P orbital. you call it 5p. You can have -1, 0, +1. So you have 3 orbitals. If your L is 3, you call it F orbital. N is 4, you call it 4F. So you can range from -3, -2, -1, 0, 1, 2, 3. Totally have 7 orbitals. That's how you determine the different names of the individual orbital. Those individual orbitals, you call them subshell, also called sublevel, subshell, S-H-E-E. This essentially determines the quantum number. Based on the quantum number, you determine the name. This slide, I have several wrong names. You never have 1P. You never have 2D. You never have 3F. So what I have over here, so this 1P doesn't exist. So L must be one number smaller than N. So the B and C, the values are right, but it's wrong name. If L is 3, you call it F orbital, it's 4F. If L is 1, you call it P orbital. So P orbital. The last one, it is 3P, but this ML can be multiple values. And follow the third couple slides show you what's the shape of your 1s, 2s, 3s, and the P orbital, Px, Py, Pz. And the D orbital, you have dxy, dxz, dyz, dxz, dyz, dxz, and dxy, dxy, dxz, dyz, and dx squared minus y squared and dz squared. So that's totally the different shapes of orbital. That will conclude our lecture for today. Thank you so much. You have a beautiful day.